Hello, I am Pranay. Today I am going to discuss about moment of inertia of an ellipsoidal revolution. So, in this lecture, at first I show you how to calculate moment of inertia of a disk. Okay, then I move on to calculate the moment of inertia of an ellipsoidal revolution. So, if you know how to calculate moment of inertia of a disk, then you can skip the first part of this lecture and move on the second part of this video, where I am going to show you how to calculate the moment of inertia of a ellipsoidal revolution. Okay, for the case of continuous mass distribution, moment of inertia I, which is equals to integration dm r square. Okay, now I am calculate the moment of inertia for our disk. So this is our disk and it is its principal axis. Okay, so first of all, let's a small elementary part of this disk. Okay, so the radius of the disk is capital R and mass of the disk is m, and from the origin at the distance x we assume a dx element. Okay, so what is the area of this elementary dx element? So pi x square. So area of this elementary dx element is pi x plus dx whole square minus pi x square. So which is pi x square minus plus 2 pi x dx plus dx whole square minus pi x square. So this term is cancelled and this is very small, so we can neglect it. So the area of this elementary part of this disk is 2 pi x dx. Okay, so moment of inertia I, which is equals to integration dm r square, and the integration is 0 to r. Okay, so this is not r, this is dmx square. So what is dm? And the dm is rho into dv. So rho into 2 pi x dx into 1. Okay, so rho 2 pi x dx. Put the value x square into rho 2 pi x dx, rho 2 pi x cube dx. Integration from 0 to r. Okay, so the rho is m by pi r square. So m by pi r square into 2 pi. So after integration, this term gives the value of this. So this is cancelled, and this is also cancelled. So m r square divided by 2. This is the moment of inertia. This is the moment of inertia when the principal axis is along z axis. But for the case of when we try to find moment of inertia along ixx or along iyy, so the moment of inertia along ixx, which is equals to using perpendicular axis theorem, ixx plus iyy equals to izz. So 2ixx, because ixx and iyy component are same, as the disk is symmetric, so we know the value of izz, m r square by 2. So the final answer ixx, which is equals to m r square by 4. Okay, so this is also the value of iyy. Now I am going to discuss about the moment of inertia of a ellipsoid. Okay, so this is an ellipsoid. This is x, this is y, and this is z. And let's assume the radius of the ellipsoid is r at its origin. Here the radius is r, and this height is h, and this height is minus h. Here is the origin 0, 0. Okay, so as we know, the equation of ellipse, okay, ellipse x square by r square plus y square by z by r square plus z square by h square, which is equals to 1. So let a elementary part whose breadth is dz here or here, assume a elementary part whose radius is smaller, and the breadth is dz. Okay, now we can integrate from plus h to minus h, then we can find the value of moment of inertia of a ellipsoidal revolution. So this is rotate along this, about this. So first of all, we can find the moment of inertia along z axis. So x square plus y square divided by r square plus z square by h square equals to 1. So this is small r square by capital R square plus z square by h square, which is equals to 1. So what is the value of small r? Small r is 1 minus z square by h square into r square. Okay, so write down this side, r square, which is equals to r square 1 minus z square by h square. So the moment of inertia of this elementary part in this ellipsoid, so di, which is equals to integration half dm r square. Why? Because along the principal axis, when we take the principal axis along z axis, then the moment of inertia of a disc is 1 by 2 m r square. That's why we start to calculate moment of inertia of this ellipsoid from this, which is equals to dy equals to half integration dm r square. So what is the value of dm? We know that the r square is this. And what is the value of dm? Dm is simply rho into pi r square dz, where this breadth is dz and the radius of this elementary part is r. So half integration dm rho pi r square dz, this is r to the power 4, rho pi r to the power 4 dz. Okay, so what is the value of r to the power 4? The value of r to the power 4 is r square 1 minus r to the power 4 1 minus z square by h square in a whole square to dz, which, and the rho, what is the value of rho? Rho is m by 4 by 3 pi r square h. So start to calculate this. The integration should be minus h to h, okay. So this is 0 to I. Okay, so I equals to this, and r to the power 4 is a constant, so we can integrate just this term. So minus h to h, 1 minus z square by h square, 2 plus z to the power 4 by h to the power 4 into dz into r to the power 4 rho pi by 2. This I equals to. So after integration, z minus 2 z cube by 3h square plus z to the power 5 by 5h to the power 4, and after put the value from minus h to h, rho pi r to the power 4 divided by 2. So here 2h minus 4h plus 2h by 5. Okay, so now I rho pi r to the power 4 divided by 2. Now it's okay. So this value is 2 is common and 2 to cancel, 2. The value is 1 minus 2 by 3, 1 minus 2 by 3 plus 1 by 5, which is equals to 15 minus 10 plus 3, which is 8 by 15. So the value is m by 4 by 3 pi r square h r to the power 4 h into 8 by 15. So h cancel, r square, this is 2, this is 5. So the answer is m r square 2 by 5. M r square 2 by 5. This is the moment of inertia of an ellipsoidal revolution when the principal axis is z. So this is I z z, which is equals to 2 m r square divided by 5. Okay, now I am calculate the moment of inertia of this ellipsoidal revolution, or the ellipsoidal revolution along the y component, along when the ellipsoid it is rotating along this. So what is the value of di? So the value of di is integration 1 by 4 dm r square plus m z square. This is now the diagram is same, and we assume a small element at the distance of z. Okay, so now the inertia is 1 by 4. Why? Because we calculate that the when we revolve, we rotate our disk along z axis or along x axis or y axis. So let's say this is y axis and this is x axis. Then we know that the moment of inertia I, which is equals to 1 by 4 m r square, where the radius of the disk is r. Okay, so that's why we write 1 by 4 m r dm r square plus dm z square. So after integrating it, okay, we know that this term 1 by 2 dm r square, this term is known term. This calculation is similar to the previous ones, so we can calculate just this. So we write the value of this, which is 1/2 into 2 by 5 m r square, from integration from minus h to h. Okay, so this is cancelled, 1 by 5 m r square. So the dm z square is the second term, which calculate from z square rho pi r square dz. Okay, integration minus h to h. So what is the after integration, the r square is capital R square 1 minus z square by h square. Okay, into z square integration rho pi dz. So r square is constant, so write it here, minus h to h. So z to the power z square minus z to the power 4 by h square dz, integration minus h, integration h to minus h rho pi r square, and the integration value is z cube by 3 minus z to the power 5 by 5 h square. This is 2 h cube by 3 minus 2 h cube by 5. So the value is 2 h cube by 15 is equals to 4 h cube by 15. Okay, am I right? So this is 5 minus 3. Okay, fine. So the value of this integration is basically 1 m by 4 by 3 pi r square h pi r square into 4 h cube divided by 15. So 4 cancel, r cube by r square, h cube h square, r square cancel, pi cancel, 4 the 5. So the value is 1 by 5 m r square. So 1 by 5 m r square plus this is m term h square 5. Okay, these are the terms. So the answer is 1 by 5 m r square plus h square. This is the moment of inertia along y axis. So IYY, moment of inertia of the ellipsoidal revolution when we rotate the ellipsoid along y axis or x axis, whatever, the inertia is same. IYY is 1 by 5 m r square plus h square. Okay, so that's all.